In section 1.4, we're going to take a lot of the things we've learned in past sections and use them to do something called curve sketching. The nice thing is there's no new concepts. That doesn't mean that it's necessarily easy. There's a lot to it. So let's just review some of the stuff that we've done. Domain of a function. Just a quick reminder on domain of a function. The two things you want to look for is zeros in the denominators. We don't want any zeros in the denominators. The second thing is you can't have square roots with negative numbers. So just a real quick reminder, if you have a square root, the inside cannot be negative. So we always took the inside and we say that it's greater than or equal to 0. And if you solve that, that can tell you what the domain is. So those are the two things you're worried about, domain. We've done a lot with vertical asymptotes. There's a vertical asymptote if you reduce it and you still get a 0 in the denominator. Then that means that you have a vertical asymptote. A whole is when in the original function, x cannot equal something, but after you reduce it, there's no longer a restriction. So basically the factor reduces out. I'll show you some examples of that. To find an x-intercept, you plug 0 in for y. To find a y-intercept, you plug 0 in for x and solve. In behavior, that's just 1.3. That's what we just barely did. Right? We're comparing the degree of the top to the degree of the bottom. And then trying to find out what happens as x gets really big. Asymptotes, okay, even and odd asymptotes. That's right. Once we look at it, we can decide if both sides are going up or both sides are going down. So we can take that. So those are all things that we've talked about and that we've done, but we're going to put them all together to help us to graph these curves. So let's just start here. We're not actually going to graph these first few. We're just going to go through and review those things we just talked about. So on number 1, we want to find the domain. Whenever you go to find the domain, we're going to start by factoring the denominator. And that will allow us then to figure out what x cannot equal. Right? So to get a 0, the denominator, it would be 0 if x equals 0 or x equals 2. So let's put that down. X cannot equal 0 or 2. Okay, let's check and see if there's a vertical asymptote. To do that, you need to see if the function reduces. So check to see if you can reduce the function. I've got an x plus 2 on top, an x minus 2 on the bottom. Unfortunately, those don't reduce. So there are no holes in the graph. That means 0 and 2 are both vertical asymptotes. When you write the equation, we should write it as x equals, right? It's the equation of a vertical line. It's x equals 0, x equals 2. End behavior. For end behavior, we compare the degree of the top and the bottom. The highest degree term is a degree 1 on top, a degree 2 on the bottom. The bottom's bigger. It's going to get bigger as x gets really big. It's going to get bigger faster, which means I'm going to have a horizontal asymptote at y equals 0. Okay, so what it's going to come out to. Okay, let's do number 2. So g of x equals 2x cubed over x plus 3 squared. So again, domain. Start by looking at the denominator and saying what can x not equal. Let's see, so negative 3, right? X cannot equal negative 3. That would make that equal to 0. Decide if it's a vertical asymptote or a hole in the graph. The x plus 3 does not reduce. That means it has to be a vertical asymptote. End behavior. So we compare the degree of the top to the bottom. Make sure it's the highest term. X plus 3 is not a term. So the top's going to be 2x cubed. If I were to multiply out that bottom part, my highest degree term would be an x squared. There'd be x squared plus 6x plus 9, but we only care about the x squared. Okay, compare the degree. The top is bigger than the bottom. What that means is the top's going to overwhelm it. So this one's does not have a horizontal asymptote. It just keeps getting bigger. So to do end behavior, we can't write it as a horizontal asymptote, but we can do this. We can say as x goes to infinity, y goes to. So if I plug in really big numbers, I have to decide if it's going to positive infinity, it's going up, or it's going down to negative infinity. Well, if I plug in really big positive numbers, the top will be positive, and the bottom will be positive. That means it's going to positive infinity. Okay, the second part, what happens as I go to the left? So as I go to negative infinity, what does y do? So plug in negative numbers. If I plug a negative number in here, say like a negative 100, and I cube it, I'll get a negative out. On the bottom, if I square a negative, I'm going to get a positive back out. And a negative over a positive is a negative. So what that means really, as I go to the right, as x goes to infinity, y goes to infinity, so the graph goes up to the right. As I go to the left, x goes to negative infinity, y goes to negative infinity, which means it's going down. Okay, number 3. They have it all factored for us down here. This one does reduce, but before we do that, let's figure out the domain. So what would make those two factors equal to 0? So that would be x cannot equal -2 or 2. This h red stands for h reduced. You'll see that a lot in the book. So if I want to reduce this, I've got an x minus 2 and an x minus 2. So I'm going to rewrite that up here. My new reduced form is equal to x plus 4 over x plus 2. Okay, so now go down for a vertical asymptote or a hole. This is how we decide. So if you reduce it, if I still get 0 in the denominator after I reduce it, the factor is still there, that means that will be a vertical asymptote. So it's going to be a vertical asymptote at x equals -2. That's supposed to be an x there. The hole in the graph. The hole is what reduced out. So originally we said x could not equal -2, or sorry, over here, could not equal +2, but then that reduced. So when I look at the reduced form, now x could equal a +2, and so that means that +2 is a hole in the graph. It reduced out. So it's got to be 2 something. Because it's a hole, we want to give the coordinates. So to find the y coordinate, all I do is take the 2 and plug it back into my equation, my reduced equation. 2 plus 4 is 6. 2 plus 2 is 4, so I get 6/4. You could put 3/2 or 1.5 would be fine. All right, end behavior. So to check end behavior, I compare the term with the highest degree. Well, they're both x squareds. And there's a 1 in front of them. So what's going to happen, right? They're tied now. They're going to basically undo each other, cancel each other out. So now I'm left with a horizontal asymptote. Man, that is not one to write there. A horizontal asymptote of x, not x, it's horizontal, sorry, of y is equal to 1 over 1, which is 1. So those are stuff we've done recently, but it's a good review, and that will help us as we go through and graph these functions. So in the book, it has this curve sketching recipe. Basically, they're just steps you can follow to get enough information, hopefully, to get a good graph. So step number 1 always is to give the domain. Step 2 is to reduce f of x. And when you go to do that, a lot of times you'll have to factor if it's not already factored for you. You got to tell if they're vertical asymptotes or whole. And just remember, vertical asymptotes, right? That's when the factor does not reduce. Wholes are when the factor does reduce. Find the x and the y intercepts, end behavior. Number 6 is check for symmetry. You don't have to do that all the time, but that could be helpful. A lot of times you can tell right away from a graph just because of where the asymptotes are and different points are that it's not symmetric. But if you think it might be, that can make your job easier. It can make it easier to graph if you know that it is. Remember how we check for symmetry, right? We can plug in opposites, like you could plug in 1 and -1 or 2 and -2. And you should, if it's symmetric about the y, you get the same thing back out. If it's symmetric about the origin, you get opposites back out. Find a starting point. Sometimes there's just not enough information, so we can plug in a point or two to figure out where to start with my graph. Okay, and then we can draw a sketch of it. Okay, so we've got 3 examples here we're going to go through. And we're going to, just to show you how we can use that curve sketching recipe. So first thing is the domain. If you look at this function, though, this one, right, the 2 things we said we have to worry about is getting a 0 in the denominator. Well, this one's not a fraction. It's not rational, so there's no 0 in the denominator. There can't be. There's no denominator, I should say. There's no square root, so I don't have to worry about getting a negative inside the square root. So since there's no restrictions, the domain on this one's going to be all real numbers, or you could say -infinity to infinity. So that means I don't have to worry about vertical asymptotes either or holes in the graph. So we're going to skip right down to x and y intercepts. Remember, to find an x-intercept, you put 0 in for y. So we'd go 0 equals x times x minus 1 times x plus 2 squared. Okay, and then you want to find out, well, and because it's already factored, this is pretty easy, but we'll make each of those factors equal to 0. So that would be x equals 0, x equals 1, and x equals -2. Now, since it asks for x-intercepts, let's write them as coordinate points. So x was 0, y was 0. X was 0, x was 1, y was 0, and x was -2, y was 0. So it's got 3 x-intercepts. Let's put those points on the graph. So we know it crosses at 0, 0, at 1, 0, and at -2, 0. One other thing, this is like a review of Math 3. We haven't talked about it in calculus. It's something you covered then, is that if you look at the degree of your factors, what I mean by that is that's x to the first, or x minus 1 to the first, and that one's x plus 2 squared. If your degree of the factors, or the power there, is even, that means the graph will actually bounce off. So what I mean by that is, you know, if this is my x and y axis, it will come up and just touch and go back. If it's odd, it will actually cross. So what that, we can actually look up there and tell that at 0, 0, it's x to the first power, it's going to cross there. At 1, 0, it's x minus 1 to the first power, it's going to cross. At -2, 0, it's to the second power, it's even, so it's going to bounce. All right, let's find the y-intercept. And we actually already have it. Normally you'd plug 0 in for x, which is pretty easy, but we already know it crosses on the y-axis at 0, so it's also 0, 0. Okay, let's do end behavior. We can't compare the degree of the top to the bottom because there isn't one. So what that means is this graph will either go to infinity or to -infinity. So let's check which one. So we're going to say as x goes to infinity, what does y do? That means as I go to the right. As x goes to -infinity, what does y do? So if you look back up there, think about this. If I plug in really big numbers for x into here, I'm going to get a positive. This x will be positive. Plug a really big number in there, I'm going to get a positive. And I plug a big number in there, I'm going to get a positive. Well, if I multiply 3 positives, I get a positive. So what that means is my graph over here is going up to the right. Okay, let's think about what happens when you plug in a negative. If I plug in a really big negative number, the first one's going to be negative. The second one's going to be negative. So we're going to multiply a negative by a negative. This one right here, a really big negative number plus 2 will be negative, but when I square it, it comes out to be a positive. So I have a negative times a negative, which is a positive, and a positive times a positive, which is a positive. So as x goes to the left to -infinity, y will also go to infinity. Okay, so there's our end behavior. Now let's take all this info. Whoops, sorry about that. Let's take all this info and draw a sketch of what it looks like. Oops, having a little technical difficulties there. Sorry about that. I'm just going to slide these, if I can get it to. That's okay. Maybe it won't. Okay, so I know, by the way, so I know we said go to the left, it's going up. So we said at -2, it has to bounce. So what the graph's going to look like, it's going to come down, it's going to bounce at -2 and go back up. Then it has to cross there, and then it has to cross there. So my graph's going to look something like that. Now what I don't know is right here on that part of the graph right there that I'm outlining, I don't know how high or how low that goes. I could plug in some points, but we're not worried about that. I just want the basic shape. Same thing down here. Like I don't know how low that graph goes, but what I do know is that it's you know, the basic shape, and that's all we want. We don't have to get too detailed on this. Okay, let's look at one that is rational, that does have a fraction. They're a little bit trickier. So if you look at this one, luckily that's factored for us because it doesn't look fun to factor. Let's start with the domain. So what would make each factor equal to 0? So that would be x cannot equal 0. That would be 1, and that one would be 3. Now we've got to decide which one of those are holes in the graph and which one of those are vertical asymptotes. And the way we do that is we reduce the function. So let's reduce it. So g of x reduced, that x will cancel with one of those x's. So I have an x to the first on the bottom. That x minus 1 will cancel out with one of those. So I have an x minus 1 left on top. Those two, I almost canceled those out, but they don't, right? I've got an x plus 3 and an x minus 3. They will not reduce. So let's just leave those alone. So I've got x plus 3 squared on top. And I've got x minus 3 squared on the bottom. Okay, so here's how we tell if they're vertical asymptotes or holes. So I look back up. On the original function, we said that x could not equal 0, 1, or 3. On the reduced function, x cannot equal 0 or 3, but x could equal a positive 1. So since the x minus 1 went away completely, that means 1 is a hole in the graph at 1 something. The vertical asymptotes then are at x equals 0, x equals 1, and x equals 3. Let's also write down with, whoops, I almost made a mistake there. I'm sorry. It's not at x equals 1, right? The x minus 1 completely reduced out. It's no longer here. That means that it's not a vertical asymptote. It's a hole in the graph. By the way, we can tell if 0 and 3 are odd or even asymptotes. We talked about that in 1.3. X equals 0, that comes, look at the reduced form when you do this. It's x to the first power, so that means 0 is odd. X equals 3, x minus 3 squared is to the second power, so it's going to be even. That will be helpful to us. Let's figure out what the hole is. So remember, to figure out what the hole is, I take 1 and I plug it back into my equation. So if I plug 1 into there, I get what 1 minus 1 is 0. 0 times, that'd be 4 squared is 16. I get a 0 on top. On the bottom, I get 1 times 1 minus 3 is negative 2 squared is 4. So we end up with like a 4 on the bottom. 0 divided by 4 is 0. So over here at 1, 0, there's a hole in the graph. And we know at x equals 0, there's a vertical asymptote. And at x equals 3, there's a vertical asymptote. Okay, let's find the x-intercepts and y-intercepts. So to find the x-intercept, we plug 0. We can use the reduced form. So let's plug 0 in for y right up there, and I'd get 0 equals x minus 1 times x plus 3 squared all over x times x minus 3 squared. All right, think about when a fraction equals 0. A fraction will only equal 0 when our numerator equals 0, right? 0 over something equals 0. So all I got to do is figure out when that equals 0. It's already factored, so that would be at 1 and at negative 3. Well, we already know at 1 there's a hole in the graph, so that's not going to be an x-intercept, but we can put down at negative 3 there's going to be one. So when x is negative 3, y is 0. For the y-intercept, we plug 0 in for x. The problem is you can't plug 0 in for x. We said x cannot equal 0. There's a vertical asymptote there. That means that there is no y-intercept. Okay, end behavior. To do end behavior, we need to find the highest term on top and the highest term on the bottom. I didn't mean to erase all of that. Let's see, there was a hole at 1, 0. There was no y-intercept. And the reduced form was x times x minus 3 squared and x minus 1 times x plus 3 squared. All right. So you can either use the original function or the reduced form to check end behavior. It doesn't matter. They'll have the same end behavior. I'm just going to use the reduced form. So on the bottom, I'd have x times x squared. It'd be x cubed on top. On the bottom, I'd have x squared times x. It's x cubed on the bottom. Well, so they're tied. They both have a 1 in front, so I take 1 over 1. So my end behavior is I have a horizontal asymptote at y equals 1. Okay, so come over here at y equals 1 up here. We know there's a horizontal asymptote. Sorry about the pause there. We had some technical difficulties. While I was fixing that, though, I did notice something. Hey, this top one was not x plus 3 squared. It was x plus 3 cubed. And that changes our end behavior. So let's go back and fix that. I apologize. So the top would be x times x cubed would be x to the 4th up on top. Sorry about that. On the bottom, it would be x times x squared, so x to the 3rd. So the top's bigger than the bottom. That means that there is not a horizontal asymptote. So instead, I'm just going to say what happens as I go to the right, and as x goes to infinity, what happens to my y values, and what happens as I go to the left. Oops, as x goes to negative infinity, what happens to y. So just think about this for a second. Look at my reduced form. If I go to the right, if I plug in a really big positive number, this would be a positive times a positive, so I get a positive on top. On the bottom, I'd get a positive times a positive, so you have a positive on the bottom. So when I divide those, it will end up being a positive infinity. If I go to the left, this term is going to be negative. If I take a really big negative number plus 3, it will be negative to the 3rd power is negative. So I have a negative times a negative, which is actually going to give me a positive on top. On the bottom, I have a negative times, and this x minus 3 squared, because it's squared, is going to be a positive. So a negative times a positive, which actually is going to give me a negative. So I say as x goes to infinity, y is going to go to negative infinity down there. Okay, so let's see if we can figure all this out. So we're going to come up here. If you think over here in the right quadrant over here, what's happening? It never crosses the x-axis. So it could either do one of two things. It could come up this way, or it could come down this way. The problem is it can't be this one. Let me outline it. It cannot be this one, because if it came down that way, comes along my horizontal asymptote and goes down that vertical asymptote. If it was that, then it would have to cross the x-axis, but there was no x-intercept over there. So since it never crosses the x-axis over here, that means the graph has to be coming along the horizontal asymptote over here, and it has to curve up that direction. Okay, over here we said that at x equals 3, it was an even asymptote. So remember what we talked about. That means that if this side is going up, this side has to go up too. So that side has to go up too. That means it's going to come down, drop down here, right? There's a hole in the graph there, which means it's going to continue down that direction. If you look at x equals 0, it's an odd asymptote. So right here, if this side is going down, that means this side has to be going up. And then I have the horizontal asymptote, so it's got to come along, and it's got to turn that direction, going along that horizontal asymptote. So if you have a calculator there, take just a second and graph it. Make sure you put this top part in parentheses like this, divided by that. And you ought to see a graph pretty similar to that. It's not going to show the hole, but it should have the same basic shape other than that of everything we've done there. All right, let's do that last example. So I have x plus 1 over the square root of x squared. So start with the domain. First of all, what would make the bottom equal to 0? And that would be 0. So x cannot equal 0. Second thing is, look at the inside of the square root. I've got the x squared, right? We said if you have a square root, the inside has to be greater than or equal to 0. So we need to solve that. Well, to solve that equation, normally to solve that, you could treat it like an equation, set it equal to 0, take the square root of both sides. But in this case, if you just think about it, x squared is always going to be greater than 0 unless it's equal to 0. It'll never be negative, right? Because you're squaring it. So what that means is there are no restrictions from the square root, because x will always be, no matter what I plug in for x squared will always be greater than or equal to 0. Okay, so our only restriction on this one is that the domain cannot equal 0. Hey, vertical asymptotes, just a quick reminder, if I plug 0 in, I get 1 over 0. That means 0 is not a hole in the graph. That means 0 is a vertical asymptote. So x equals 0 is my vertical asymptote. There aren't any holes, right? There's no factors that reduced. The x-intercept is what makes the top equal to 0, right? I want this to be 0 over here. That means the top has to equal 0. That'd be negative 1. The y-intercept, for the y-intercept you plug 0 in, but we can't plug 0 in. We said in our domain, right? There's a vertical asymptote, x cannot equal 0. That means there is no y-intercept. End behavior. Okay, you got to remember how we did this. We did these back in 1.3, but to check end behavior, I compared the degree of the top to the bottom. So that's x to the first. If I take the square root of x squared, that's also x to the first. So since they're tied, x to the first, you look at the numbers in front. So there's a 1 there. This is the tricky part, is remember, it could be plus or minus 1. And usually what happens is as I go one direction, it's going to approach either 1 or negative 1. And if I go the other direction, it will do the opposite. So usually they have two asymptotes when you have a fraction with a square root in it. So let's just check and see what happens. So I have to decide if it goes to positive 1 or negative 1. So as x goes to infinity, as I go to the right, what happens to y? Well, if I plug in positive numbers, I'll get a positive on top and a positive on the bottom. So that means it's going to positive infinity. Let's go to negative infinity. As x goes to negative infinity, that means I plug in really big negative numbers. Well, the top is going to be negative. The bottom, when I square it, it's going to give me a positive, and take a square root, it's still going to be a positive. So I have a negative over a positive. So hey, I shouldn't have put, I'm struggling today. It's not y goes to infinity, right? I was choosing between a positive 1 and a negative 1. It came out to be a positive, so we'll go to a positive 1. Sorry about that. As x goes to negative infinity, as I go to the left, y is going to go to, and again, when I plugged in a negative number, a really big negative number, I got a negative over a positive, which is a negative. So it's going to go to -1. So let's put all this on my graph. I come over here, there's a vertical asymptote right there. There's an x-intercept at -1, 0. There was no holes, no y-intercept. My end behaviors, I do have, going to the right, I have a horizontal asymptote at 1. Going to the left, I have a horizontal asymptote at -1. So kind of think about what happens here. I know it has to cross here. I know it has to go on that vertical asymptote. So it's got to be going up that direction, and then it's going to curve down that way. Over here on this opposite side, it's got to be up in this part. And the reason why is, I'll do it in a different color. If I were to draw it down here like I'm doing in red, right, if it went that way, then it would have to have an x-intercept over on this right side, right? It would have to cross the x-axis, which it doesn't, right? We found the x-intercepts. The only x-intercept it had was at -1, 0. So my graph's going to look something like that. Sometimes you'll see this where it says, hey, what's this? Where's the starting point? First, if you do ever get stuck and you're not sure, plug in a number. Like we could, for example, plug in 1. When x is 1, if I plug 1 into that equation, I get y equals 1 plus 1 is 2 over 1 squared square root, which is 1. So if I plug 1 in, I got 2 back out, right? And so that would give me a starting point. So if you ever if you're ever not sure what it looks like and you need some more info before after you got your framework there, your asymptotes and your and your intercepts, that's one strategy is you can take a point and plug it in there. All right, so that's it for 1.4. Hopefully that made sense. Sorry about those couple mistakes there. I should quit doing videos late at night. Anyway, if you have questions, make sure you let me know. These are kind of tricky. They take a long time. You'll see the assignment is pretty short on these. I think you only have really 5 or 6 problems you're doing curve sketching with. Then it jumps into doing a bunch of review on limits. But make sure as you go through there, keep track of your questions, let me know so I can help you through that. Thanks, guys.